roughly?
Yeah, it was 2 years ago, 2019.
Yeah. So I'm really looking forward to the talk. But over to David. Why don't you do the actual introduction?
Cool. Yeah, thanks for the very brief pre-introduction, Kareem. So Cristian is a postdoctoral researcher at the Université Catholique de Leuven, as you might have heard him just say just now. And also, like you might have just heard him say, from the 1st of December, he's going to be moving to do a postdoc at the University of Lausanne. Cristian works predominantly on philosophy of physics, philosophy of time, and the metaphysics of science. And today, we're very excited to hear his talk titled, "What Can We Learn from Time Reversal Invariance?" So I will hand it over to you, Cristian.
Okay, first of all, thank you very much for the invitation. I'm very happy to be here with you. As I said before, I mean, it's a pity not to be there in person, but okay, in any way, I'm very happy. So yes, this is the title, "What Can We Learn from Time Reversal Invariance?" I have two answers. I mean, I have two answers. One is stronger than the other. The first answer I would try to give you is that what can we learn from time reversal invariance depends. It depends on some previous assumed philosophical framework. I'm trying to give an explanation of what we mean by that. But the second answer, that is probably that is the stronger answer, is that probably is not what we can learn from time reversal invariant. Probably is not too much, right? And this is an answer that is more related to a general view about symmetries in metaphysics of science, but also in philosophy of physics in general. So I will try to frame my discussion in these two answers. So let me first start with some background, just to have a common ground to discuss. We have a philosophical problem. The problem is the problem about the direction of time. Probably you are already familiarized with that, but the overall idea is that people interested in the philosophy of time direction usually raise this question: whether our world comes equipped with a direction of time, that is, whether we can distinguish in a substantive way between the past to future and the future to past direction. Okay, this is a very simple. Okay, this is a very simple formulation, but this is I think, interesting philosophical problem. When you look at the literature in philosophy of physics and philosophy of time, usually this problem is introduced in terms of time reversal invariance. The idea is that you can reformulate the problem in terms of symmetries. So now the question, the philosophical problem now becomes something like whether our fundamental laws are time reversal invariant or not. So there's this idea that we can learn about time's direction by looking at the time reversal symmetry in our fundamental theories. So this is what I think seems to be going on behind this reformulation of the problem. On the one hand, we have a symmetry that is a property of our physical theories, in particular in the formal implementation of the physical theories. And on the other side, we have something about the ontology of the world, about for example, whether time is directed or not in the ontology. So it seems to be this connection between these two extremes, right? And it's to be an inference that is trying to connect these two extremes. So we have the philosophical problem. We have this reformulation that is very popular in the literature, and we need something like an inference that tries to connect one side with the other. And this is what I'm calling here the time reversal inference, or TR-inference for short. And this is a super oversimplified version, but the idea basically is something like this. We consider a set of dynamical equations of a physical theory. Then we assume that if that set remains invariant under time reversal, then there's a sense in which the theory doesn't exhibit a fundamental or inbuilt direction of time. Then usually the inference goes, we find that probably the majority of the physical theories of the dynamical laws that we know so far are invariant under time reversal. And then we can explain what it means And in general, what we want to say is something like, well, in this equation, we can freely vary t by minus t, for example, and keep the structure of the dynamical laws unchanged. And then we can explain even this further by saying, well, it has something to do with some non-objective, redundant, or undetectable, unobservable property that we are introducing in a physical theory. By some epistemic premise, we can draw a philosophic, ontological conclusion about time. If all these premises are met, then we can say that the theory at stake doesn't exhibit time direction, and therefore the time direction is not fundamental according to a theory T. This is more or less, I mean, this is oversimplified, but it's more or less the dialectic that usually you can find in many of the debates about time direction in physics and philosophy of time. Okay, there is many different premises here. You have some epistemic premises, some more metaphysical conclusion, some interpretative tasks trying to show us what it means that something is invariant under some information, and we try to connect this idea with objectivity, with redundancy, with detectability, or whatever. But also we have some formal premises. The idea that we know or we learn from physics that some set of equation is invariant under some transformation. In this particular case, under time reversal. This is something that is not in generally put into question, but it's something that you take from physics textbook, for example. So I'm gonna focus on these premises, right? There is a lot of debate about, for example, the notion of invariance, of symmetry in relation to objectivity, redundancy, and so on. But I want to focus on the formal premises. How can we know that asymmetry is established in a physical theory? How can we know that a particular dynamical equation, for example, is symmetric under some transformation? And the particular case is going to be time reversal. So what are the aims in general? They are not very great, but this is something just to have a guide. First, well, I would like to convince you that we should uncover some assumptions that are working behind the TR-inference. Second, based on these assumptions, try to draw some lines of resistance to the inference. This connection between symmetry, time reversal, invariance in particular, and something about the ontology, time direction in particular, well, could be I mean, put into question. And I would like to draw some ideas that in which way this could be done. And more general, I would like to shed some light on the nature of time reversal symmetry. What is the role that we expect time reversal symmetry to play in physics, but also it could be extended to symmetries in general. So I will try to say a bit about all these three things. So this is the outline of the talk. So let's go to the first point. I'm gonna be quick on this because you probably already know what's time reversal, but the idea is very intuitive, at least at first glance. What you have is, for example, a physical system, and you consider the evolution of the system from T0 to T1, and it's described according to some physical law, right? And then you think, well, okay, what about time reversal? First, time reversal is an action, an operation, something that we do on the physical system or on the law that describe the evolution of the physical system, and try to reproduce the idea of taking the system back to the initial state, or try to reverse it, or try to represent the evolution going backward in time. This is what time reversal tries to capture. Formally, the idea of evolving backward in time. So what we expect is we have a system evolving from T0 to T1, and then we apply time reversal. We expect the system to go from T1 to T0, and we have now two different evolutions: the original evolution, the time reverse evolution, And then we can ask whether the evolution are equally solution of the same law. And in general, the idea of symmetry, or in this case, time reversal symmetry, is the idea that, well, if a dynamical equation, for example, is time reversal invariant, then it transforms solution into solutions. This is the most general, probably, definition of what is asymmetry, and in particular, what is time reversal. So what can we philosophically learn from it? From the idea that time reversal is an operation that transforms a solution into a solution. It's trying to capture the idea of evolving something backward in time. Well, first, I think that we can learn nothing. Nothing in the sense that this is just mathematics. It's just an operation that is transforming some quantities appearing in a differential equation, for example, and try to reproduce structurally the idea of going something backward in time. But there is nothing related to a concept of what it means something to be symmetric. Just that an operation transforms solution into solution says nothing about the nature of the relation between, for example, two models related by a symmetry. For philosophical conclusion, we need some philosophical premises, and we cannot expect to have some rich philosophical conclusion from just mathematics. We need to do something else. So in general, when we take this idea that asymmetry takes solution into solution, we also, in general, try to add something to this, try to rephrase the relation in terms of some observational, representational, modal, structural equivalence. But this should come from elsewhere. This is a way in which we can just give a more substantial or meaningful definition of symmetry. But it's not enough with the idea of transformation just mapping solution into solution and non-solution into non-solution. We need some philosophical work to give a more substantive definition of symmetries. And this is how, so far, I mean, how many people discuss the idea of what does it mean to have a symmetry, I mean, in a philosophical sense. Of course, we have the very abstract definition, in this particular case of time reversal symmetry, that we have a solution and then we transform it in a different solution that is the time reverse of the first one. But we need to say something else to give a more substantive notion. And there are many discussions about that. But this is, I think, this is fair. I mean, I completely agree that a philosophical and philosophically interesting notion of symmetry requires some idea about observation, about the detectability, modality, probably redundancy or whatever. But I'm not going to focus on that. I rather want to focus on the idea of the transformation. The idea of transformation is try to elucidate what is time reversal in itself. And what I mean is that try to elucidate what time reversal does, what kind of action should perform to deserve the name time reversal. So my first intuition about this when I started to think about this problem is that, well, I mean, if you see the formal definition of time reversal, it's just a mathematical transformation that take, for example, an observable and transform it in a particular way. But this formal implementation, this mathematical transformation, is trying to represent something. It's trying to represent a concept that is guiding the implementation of time reversal in a given formalism. So there is some previous idea of what we mean by reversing time that is being implemented in the mathematical transformation. But there's also some concept of what we expect of time reversal that is being implemented in the transformation. So if we want to study what is time reversal, it's fine, we should focus on the formalism, but we should also focus on the concept that the formalism is trying to capture. So when I started to think about this, I came up with two ideas in general. This mathematical implementation depends on some concept of time reversal, but in two different ways. One idea is that depend on our previous understanding of what is time and what is time reversal as a concept. Time reversal as a mathematical transformation is trying to represent some idea of what is time reverse something. But also the other idea is that we are trying to capture a role that we expect time reversal invariance to play in a physical theory. And these two ideas, probably there could be, of course, more, but this is the two that I thought about, are already in the implementation of time reversal in a formal sense. So now let me give you more detail about these two ideas in a concrete case that is time reversal in standard quantum mechanics. So we can ask ourselves, is quantum mechanics time reversal invariant? And by quantum mechanics here, I'm going to refer just to the bare formalism without any particular interpretation, without the collapse postulate, just the formulation in the Hilbert space and the dynamical equation that we usually recognize as the fundamental one, the Schrödinger equation. So we have this question. Then, okay, we just write down the Schrödinger equation. We know that this Schrödinger equation is the fundamental Schrödinger equation in the sense that it's the simplest expression of the Schrödinger equation. Is this formulation that covers different cases, the simplest one. And also try to, I mean, what is within the brackets is the Hamiltonian for a system, but we consider the simplest Hamiltonian as well, with potential that is perfectly homogeneous, for example, but also without any interaction, without anything, just a free system, non-relativistic single particle, for example. So we focus on this idea. We want to investigate whether this equation is time reversal invariant. We have the law in this particular expression, the most fundamental one, and then we have to figure out what it means to time reverse the Schrödinger equation. And we have this formal implementation of time reversal in the quantum mechanical formalism. So we need to know what time reversal should do to reverse the Schrödinger equation, or to reverse the system that this equation is trying to describe. Of course, an intuitive idea is that time reversal should reverse the time coordinate. After all, it's time reversal, so it sounds like reasonable to expect time reversal to transform t by minus t. That's okay. So in the definition of time reversal, we say, okay, time reversal should do this, should transform t by minus t. What about position? It seems that position is not related to time in any meaningful sense in non-relativistic quantum mechanics. So we say, okay, time reversal shouldn't transform position in a particular way. So just when applied to position, just give the position untouched. But then we have the wave function, and the wave function is trickier. And this is how the discussion is about, because it's not a clear way in which we can see how the wave function should transform under time reversal. How it means to transform the wave function in time, to just make the wave function evolve, for example, backward. It is, I mean, we don't have a clear intuition about how that could work. But when you look at the quantum mechanical textbooks in general, there is a kind of dictum that says something like the quantum mechanical time reversal transformation must be anti-unitary. It doesn't really matter what anti-unitarity means. What is important here is that anti-unitarity is given a constraint in the form of the time reversal transformation in quantum mechanics. What kind of feature should the time reversal transformation involve should follow this dictum that should be anti-unitary. And then we know, I mean, from quantum mechanics in general, that an easy way to make an operator anti-unitary is just making that it involves, in some sense, a complete conjugation. So we demand the time reversal transformation to implement complete conjugation in some way. And we know from that, for example, any imaginary unit should flip sign, right? And from that, we can figure out that the wave function should transform under time reversal into its complex conjugate. I mean, the details are not really important. What is important is the logic that we are following to know how to implement time reversal formally in a physical theory. So we are following some guides. But now we have a nice formal definition of time reversal. What we should do, what we have to do when we are faced with a Schrodinger equation and we are asked to transform it under time reversal. We know that we should apply this transformation in the equation. And again, the details are not really important, but when we do this, when we apply this time reversal transformation to the Schrodinger equation, we realize that the original Schrodinger equation and the time reverse Schrodinger equation are equivalent are symmetric in this sense. So if they are symmetric or the Schrodinger equation remain invariant under time reversal, so the answer is of course is yes. I mean, when we ask ourselves if quantum mechanics is time reversal invariant in this particular formulation, the answer is yes, it is time reversal invariant if T, I mean, how we defined the time reversal transformation represent time reversal in a fair way. So now we can, of course, just plug this conclusion here into the argument that we saw before, and we say, okay, now we learned that the Schrodinger equation is time reversal invariant. So then we can say that there is no direction of time, and at least in a fundamental sense, via the TR-inference, because the Schrodinger equation was invariant under time reversal. I mean, and then we can just make the previous argument work in a nice way, because we learned this from investigating about time reversal in quantum mechanics. This is more or less the orthodox story, the standard way to tell how we can implement time reversal in quantum mechanics. But even though this is the orthodox, I mean, if you open up any quantum mechanical textbook, you're gonna find probably in a much nicer way, but more or less this story. There was a bunch of philosophers that complained. For example, this is a paper by Craig Callender in the 2000 that complained about this idea of how time reversal was being implemented in quantum mechanics. But also there was a book by David Albert where he said something more or less in the same line, that even though quantum mechanical textbook says that Schrodinger equation is time reversal invariant, he says that it is not, that the implementation of time reversal invariant should be different. And there is this another guy that also complained, even if he came 19 years later than the other guys, but also he complained. So why they complained? So I start to think what they complained. And I think that, okay, there are many details, but the most general answer is that this idea that the canonical way to implement time reversal, this is the story that I told before about the anti-unitarity of the time reversal operator and how anti-unitarity just constrained the properties of the time reversal transformation, is not quite right, because there would be a more natural way to represent time reversal. In this particular case, it's by a unitary time reversal operator, but the idea is that the orthodox way is not natural, and there would be a more natural way. So if this is the formal implementation, the canonical implementation of time reversal in quantum mechanics, there would be a more natural implementation that just transform T by minus T, right? Without, for example, taking the complex conjugate, and that's why the transformation is not anti-unitary. The problem with this definition is that when we apply this transformation to the Schrodinger equation, what we discover, again, the details are not really important. What we discover is that the original Schrodinger equation is not equivalent with the time reverse Schrodinger equation. So now there is a sense in which if T red now represents time reversal, the Schrodinger equation is non-time reversal invariant. And then with some logical tricks, we can just plug this idea into the previous argument, and we can make a case for a fundamental direction of time in quantum mechanics, because at some point we could defend the idea that even the fundamental Schrodinger equation is not invariant under time reversal. This is, for example, a calendar's strategy. And why, for example, and the explanation that why quantum mechanics is non-symmetric under time reversal, and therefore it has a direction of time. So when I saw this discussion, I also complained about the natural way to implement time reversal, but there was something that I didn't really get. So I asked myself, what is going on? Why we are discussing this? I mean, why this difference? I mean, after all, we are trying to just trying to elucidate how to transform something in formally in time. There could be there's something deeper going on. So I start to think about this problem. What was the reason why there was this discussion about time reversal in quantum mechanics? And I came up with two ideas or two theses about time reversal invariance. This was my first intuition, and I think that I'm still believe in that. At some point, the discussion looks like, well, we are trying to formally implement a given concept of time reversal. So we are just discussing about, or we are just having a difference about how to implement the same concept. We have calendar, Albert on the one side saying, no, the right way is this way, is to implement time reversal in this way. And we have the orthodox story saying, no, the right way is different, it's the other one, it's the canonical one. But I think that this is not the right way to frame the issue. The issue is not really about how to formally implement a concept of time reversal, but the discussion is really about what we want to formally implement. So the debate is really about the concept of time reversal, not about its implementation. To put it differently, people that complained about the orthodox way to implement time reversal in quantum mechanics they are not really complaining about how the canonical way implements time reversal. They are actually complaining about the concept that they are trying to implement. This is what I would try to argue, that they are actually disagreeing about the concept. And there are two theses why the concept is different. The thesis one is about the metaphysical of time. The concept that the orthodox way of the people that complain about the orthodox way is different because they disagree about what is the nature of time, and therefore what is the nature of the time reversal transformation. What we mean by time, what we mean by reversing something in time. The second thesis is that this concept of time reversal is being it involves a different idea about what is the role, the heuristic role that time reversal symmetry should play in a physical theory. So the concept now is relative to two different theses about the nature of time, but also about the role, the heuristic role that time reversal symmetry should play in physics. And now I will explain a little bit in detail this. So let's focus on the concept of time reversal as was defined for example, in the 30s with Wigner. Wigner gave a very nice definition of what is time reversal in quantum mechanics, but also in general. He says that the time reversal invariance, but also the time reversal transformation, it's something that when performed in a sequence should give us something like this. First, we time translate a system in what direction of time, wherever, then we apply time reversal. And then this transformation should make the system evolve, should make the system to translate in time somehow. And then when we apply time reversal again, we should obtain the original state. If that happens, we have time reversal invariance. But look that now, it seems to me that the main point here is not the nature of what time reversal should do in these two particular instances, but the focus, I think, that is on how time reversal could generate a time translation after its first application. So I'm going to focus on that. So let me give you some quotes about why this definition is fine, and what we are doing when we define time reversal in that way. This is a book about symmetries, principles in elementary particle physics by Gibson and Polar. And what they say there when defining time reversal in non-relativistic quantum mechanics, they say that in this approach, we see that no metaphysical notion of reversal of the direction of the flow of time is involved. We are led to consider time reversal processes, but not reversal time itself. Now, Valentine, in the very famous book about quantum mechanics, he says that the term time reversal is misleading, and the operation that is the subject of this section would be more accurately described as motion reversal. So now we can go back to Wigner's definition and say, okay, probably Wigner's definition is trying to follow this trend, try to define time reversal as a way to implement motion reversal. So in this sense, now it's clear that the second time translation in the definition is trying to capture the idea of taking the system back to the original state. So if time reversal try to implement motion reversal, then it makes sense to define time reversal in this way, because we need to generate, for example, the second time translation, and to complete the idea of what we mean to evolve something forward in time and then trying to evolve it backward in time. So there is this correlation between time reversal and motion or time reversal. And then we can think two different things. One is to say, well, okay, but I was worried about time reversal, not about motion reversal. So what about time reversal? I probably was mistaken, and all we know about time reversal is actually information that we get about motion reversal. So we can complain in this sense. And I think, for example, Callender complains in this particular sense. He distinguishes between motion reversal and time reversal, and saying, well, what physicists usually call motion reversal, time reversal is a different transformation, is motion reversal. But now this is a more natural way to implement time reversal, and he gives this more natural transformation. And I also thought in the same line. I also thought that, okay, there's something that in the physical discourse is not being captured by the idea of time reversal by giving us this transformation, this time reversal definition as Wigner did. But after that, I start to doubt even on my own thoughts. So I said, probably they are not giving us a different transformation, but they are assuming that they are the same transformation. And in this sense, they are assuming a relational view of time, in the sense that they don't think that there is something that is time that could be represented in a different way, but as we cannot do it, we go for a representation of motion reversal because it's the best we can do. Probably they are thinking that they are the same thing, that there's no meaning of time reversal that could be given out of motion reversal. And we already know that this tradition about relationalism is super old and have many interesting characters in the history of philosophy, for example, Leibniz. But the idea overall is that time considered without the things or event are nothing at all. And this idea is that if we are going to represent time reversal, we have to represent them in terms of things or events, and not in terms of a transformation of time in itself, because time in itself is nothing but things or events. So now if we assume this idea that it's not the case that physicists are talking about motion reversal and they are just applying a bad name, or they are just mistaken about the name, but they are really talking about time reversal, but in a relational way. And with this idea, we have two different theses. One is this is, of course, is much more complex because of relationalism has many facets, and people that disagree about, for example, what is the right ontology for relationalism. But just to give you a general idea, is that if physicists and in particular the implementation of time reversal invariance in quantum mechanics is promoted by a relational view about time, then in some sense they are assuming something like a monist ontology, in which there are only events or physical bodies in the world and their temporal relations. So there is nothing like time in itself that you need to transform under time reversal, but try to transform the things and their temporal relations. And also there is this reductionist thesis, in the sense that any temporal predicate should be explained in terms of change or in terms of motion. In the sense, the idea of time is just an abstraction or an idea in ens rationis, in Leibniz terms, that is not playing any ontological role. What is playing the real ontological role of time is change, or is motion. So if we take temporal relationalism seriously, we can give a definition of relational time reversal. And relational time reversal should more or less look something like this. And I think that now we can understand a little bit better what usually the canonical implementation of time reversal in physics work. First, of course, the transformation T by minus T is not a substantive transformation. With, for example, calendar, or even I said before that, okay, the more natural way to represent time reversal is just T by minus T. This is the whole content of time reversal. But for temporal relationalism, I think that this is not so, because T by minus T is just an abstraction. It's just a time coordinate. So it's just a reparameterization of what we should do. But it's not really doing something it's not really doing something physical, because there's nothing like time in itself. So the discussion is not really about T by minus T, but the discussion is about the dynamically relevant magnitudes that can generate the backward evolution. And in this particular case, for example, as I mentioned before, the particular transformation that can generate, for example, the second term translation in Wigner's definition. So all the power of time reversal is there, is in trying to give us the right transformation that can reproduce the idea of something evolving backward in time. But it's not really about T by minus T, right? So what was the debate according to how now I am seeing things? The debate is not about, again, whether it should be unitary or anti-unitary. It's not about how we can implement the same concept, but it's about whether we are relationalist or not about time. I think that the canonical implementation of time reversal involves some commitment with relationalism. The bunch of guys on the right side of the screen were just not accepting a relational definition of time. They were trying to promote a different view of time, and that was the disagreement was about. So this is the first thesis. This is the way in which I see that the formal implementation and the concept that is behind now is being supported by a metaphysical thesis about what we meant, what is meant by reversing time. Now, let me go to the second thesis. And the second thesis is related to the heuristic role of time reversal symmetry. Then we can see again Wigner's definition of time reversal. And this is one of the intuition I had when I read what Wigner said, that in this sense, time universal invariance is playing a more normative role in a physical theory, in particular in relation to how we can formulate the fundamental dynamical equations. Let me let me be a little bit more precise. You know that in philosophy of science has been normal to distinguish between fundamental laws and phenomenological laws. The fundamental laws, I mean, if we take, for example, Nancy Cartwright's definition, fundamental laws are usually thought of as covering laws. The simplest way to express a law so as to cover the majority of cases, the majority of instances. And so we're trying to formulate a theory in a very general way that include different models, different kind of Hamiltonian, different kind of interaction, and so on and so forth. This is a way that is part of the physical theories. The other part, of course, is the connection between these fundamental laws and the experiment and the things that we want to really explain. And this is the role that play the phenomenological laws. They are in general instances of the fundamental laws, plus a lot of approximation and suppositions, and so on and so forth. So what is the normative facet I see in the implementation of time reversal invariance in physics in general, but also quantum mechanics in particular? That it seems to be desirable for many theoretical purposes to have time reversal invariant fundamental laws. It seems that time reversal invariance plays some heuristic role in a heuristic role to formulate the fundamental laws in a specific way. So it's a non-empirical virtue we have that we want our physical theories to have, at least in the formulation of our fundamental law, as long as it's possible. So let me give you some examples of what I'm trying to mean with that. This is, again, a discussion about time reversal, but now in classical electromagnetism. This is Frank Arsenius and Hilary Greaves, and they are trying to elucidate how time reversal should transform the magnetic and electric field. And they take this textbook account about time reversal, and they say something like this. The standard procedure is simply to assume that classical electromagnetism is invariant under time reversal. From this assumption of time reversal invariance of the theory, it's inferred that the electric field is invariant under time reversal. This is the first quote. The second quote is different. Is now Bove mechanics. The Dürr and Teufel are trying to build up Bove mechanics themselves. At some point, they talk about symmetries, and they say something like this. They say a symmetry can be a priori. For example, space-time symmetry, but also time reversal symmetry are the kind of symmetries that play the role of setting the rules of the theater in which the dynamic is going to be unfolded, for example. So we need to set what is the scenario. And symmetries are a priori in the sense that we impose some rules in this scenario. And then we develop the dynamics that is going to be constrained by these symmetries. And time reversal is one of the symmetries that they consider that should constrain the dynamics, the dynamics in any physical theory. Now a third quote. This is Robert Sachs, and he says that in order to express explicitly the independence between the kinematics and the nature of the forces, we require that the transformation leave the equation of motion invariant when all forces or interaction vanish. So again, it is this idea that we are requiring that some particular expression of the laws, in this case, the fundamental laws, should remain invariant under a symmetric transformation, because they are playing some heuristic role in this particular case to express the independence between the kinematics and the nature of the forces. So this is what I'm trying to say with time reversal invariance is playing a heuristic role. We assume that for fundamental laws, time reversal invariance should be respected. And then and for that, we stipulate time reversal invariance beforehand. And then from that, we can, for example, figure out which is the right transformation that keeps the fundamental laws invariant. This is not, I mean, one could think that this is a little bit misleading, because, I mean, we are assuming, I mean, we wanted to prove time reversal invariant, but on the other hand, we are assuming it before. But I think that this is not a trick, because at the end, time reversal invariance in this particular case is playing a heuristic role in the formulation of physical theory. So it's natural to impose for fundamental laws, for example, time reversal invariance, because the point is to shed some light on, for example, as Robert Sachs says, the nature of the forces or whatever, or some particular structure. So again, going back to this dispute, the canonical implementation of time reversal, I think, is assuming somehow this idea that time reversal invariance should play a heuristic role in theory construction. That's why the orthodox implementation of time reversal is so useful, because it's the only one that keeps the Schrödinger equation invariant under time reversal. But this is a natural requirement, because it's assumed that time reversal is playing a heuristic role in theory construction, in particular quantum mechanics. But again, the guys on the right side of the screen, they were assuming something different about time reversal. They weren't thinking, I think, that time reversal invariant is something that we stipulate. But it seems to be that they are thinking something like time reversal is something that we discover in physical theory. But again, two different views about the role of time reversal symmetry in quantum mechanics. So to sum up this part, we first have the formal implementation of time reversal in quantum mechanical formalism. I said that depends on a concept of what is meant by reversing time. But when we investigate the concept, we realize that there are at least two theses that are playing a role in promoting a particular concept of what's meant by reversing time. This is the temporal rationalism on the one side, and on the other, by stipulation view of time reversal symmetry. And this is what I call in one of the papers the philosophical framework. So the implementation of time reversal invariance in quantum mechanics, and I would say in physics in general, should include at some point a philosophical framework that is giving the meaning of what is meant by the symmetry transformation. So now we can go back to the TR-inference and what this implies for the discussion that we had before about time direction and about the rephrasing in terms of time reversal invariance. So we have again the inference, and now I focused on the formal premises, and it was for me the idea that we learned from the physics, just we taken for granted that a certain theory is time reversal invariant, for example. And I would say, well, yes, it is, but you need to be explicit about what is the philosophical framework in which you are defining the transformation. There's some philosophical framework that is justifying the decision that you have to take to give a particular form to the operation that is implementing time reversal. And this is something that I think that should be very clear, also very to avoid some discussion about whether time reversal should be implemented in that way or in the other. In the end, all depends on the philosophical framework. So that's why my first answer to the question was it depends, because it depends on the philosophical framework. What we can learn from time reversal depends on your previous commitments to time reversal, but also to the role that you expect time reversal to play in a physical theory. If you are playing the same game, probably you can learn a lot, but probably you can disagree if you're playing a different game. For example, like Calendar, David Albert, or even me before we were playing. So this is the first answer. This is the first answer to the question. And now let me go to the second answer. And this is probably the new stuff I'm trying to think now a little bit more. one of the things that I mean, we have a lot of metaphysical discussion that are framed in this idea that we can learn something about ontology through symmetries. And we have this symmetry-to-reality inference, for example, and time reversal, and the time reversal inference is just a particular case of that. It's just a way to apply this schema to the idea of time reversal to learn something about the nature of time. But it seems to me that there is something like a symmetry realism assumed in the way in which the argument is usually introduced. Okay, by symmetry realism, what there are different versions. I think that there could be different versions, but I'm going to distinguish a strong version and a weaker version. The strong version holds something like that symmetries are fundamental concrete elements in the ontology. This is, for example, appearing in Weinberg, Heisenberg, Stephen French, or David Schroeder. But this idea that symmetries are part of the fundamental ontology, are aspect of the fundamental reality. A weaker way to give meaning to symmetry realism is the idea that symmetries probably they are not fundamental concrete elements in ontology, but they play an active role as a guide to what is fundamental in ontology. So there is some straightforward connection between symmetries on the one side and the ontology on the other side via this symmetry-to-reality inference. But at some point, I think that, because I'm going to tell you after this, that there is some realist commitment to symmetries if you accept something like this. So when I start to think about this idea of symmetry realism, and if these inferences really presuppose some symmetry realism, I had two caveats. And one caveat relates to the relation between symmetries and idealizations. And the second one is something that I already mentioned, but it's the idea that if symmetries are really stipulations, and I don't quite see how to frame that in a realist framework. So let me give you this argument. First, why I think that it could be problematic why I think that it could be problematic to be symmetry realist. And it has to do with idealizations. You know that symmetries in general, in their many flavors and forms, are hard to combine. They require a lot of formal work and complex modeling. We need a lot of idealization, abstraction, to isolate the system properly from the environment, to set away any interaction, but also we need to write down the equations in a very general way, as I previously mentioned, but also we need to generate this highly idealized model. So in some sense, symmetries, if we take them seriously, are properties of these very fundamental laws, or properties of these very highly idealized models. So in this case, if you see at the argument that I gave before, when I consider a set sigma of dynamical equation, I didn't introduce, and it's generally not introduced, for example, phenomenological laws, or laws that, for example, if you look at classical mechanics, involve some non-conservative forces. No, what we have to consider are only the fundamental laws. So there is this idea that, okay, we want to take symmetry seriously, but we should only look at the highly idealized models or these fundamental laws. So in some sense, if we want to take symmetries metaphysical seriously, I mean, in a realist sense, at some point that I think that it requires some kind of idealization realism, in the sense that we should take idealization metaphysically seriously as truth conducive tools. You know that there are many discussions in philosophy of science about what's the nature of idealizations, but it seems to me that if you really want to be symmetry realist, then you need something like idealization realism. Again, take idealization metaphysically seriously, that playing a role that is representing something in the ontology. But it is so if you want to say that idealization realism suppose, if you want to say that idealization should be taken seriously, metaphysically seriously, then you need to impose some further structure in the ontology to which this idealization on this, for example, Heidegger's model are trying to capture. And this, it seems to me, amounts to the reification of further structure. You need, for example, the reification of the dynamics, or the reification of, for example, the state space, the reification of the three-dimensional space, or wherever. You need to give some structure in the ontology that is being represented by the highly idealized models, which includes the symmetries that you want to be realist to begin with. So I think that this is more or less the chain of entailments that I see. You have something like symmetry realism. You want to be realist about symmetries. Then I would say, well, okay, then you need to take idealizations metaphysically seriously, because symmetries are usually only found in very highly idealized models or in fundamental equations. But then if you take this idea seriously, I would say, well, okay, but also you need something like a external structure to which these idealized models or to these fundamental equations try to describe. I think that all these come in the same package. If you are symmetry realist, you are committed to these ideas. And of course, there is nothing incoherent about that. Okay, there are many people that even friends that they could be very happy to accept all of this. But my worry is that, okay, but this is a view that is only compatible with some metaphysical frameworks. I mean, if you are humanist, for example, if you have this idea that there is no modality in the world, that you shouldn't reify the dynamics, for example, you wouldn't accept to take seriously the idea of the consequences of symmetry realism. So my first worry with this reading of symmetry realism in the terms of with this idea of symmetry realism is that, okay, it's coherent, but only if you buy more things, if you accept more ontological commitment. And this could be challenged by different metaphysical frameworks that are not happy with accepting what symmetry realism implies. In particular, for example, something like idealization realism, or any reification of, for example, the dynamics, or to postulate or to introduce some modality in the world. So this was my first worry about symmetry realism. The second worry I already mentioned, so this is going to be a little bit quick, that if symmetries are really stipulations, I think that there is no an easy, straightforward way to make sense of symmetry realism if, again, symmetries are stipulations. Because stipulations typically enter a theory in the context of discovery. They have to do with the way in which we formulate the physical theory. And we can need many different resources that they don't need to play a truth conducive role. So I don't quite see how even this is true, how symmetry realism could make sense of stipulation, mainly in the context of discovery. But also, I mean, if they are just, I mean, if symmetries are stipulation that try to, for example, to promote a particular non-empirical virtue, for example, simplicity, well, okay, you can have different stipulations and therefore different symmetries that may work equally well. I mean, in the sense that to get the data right, for example, or to be equally empirically adequate, but they are going to be different in the non-empirical virtues, for example. But this is a way of underdetermination. You have different formulation of physical theories that they have different symmetries. But if symmetries are stipulation, then they are playing a heuristic role, for example, or a non-empirical virtue, for example, there is no a worry. But if you are realist about that, you have to tell me, okay, I have two different formulations of the same theory, of a theory with different symmetries. They work equally well. Well, I should be realist about which of these two formulations. This is an old problem, but I think that symmetry realism just make this problem worse because now you are introducing a new variable for under determination. And from a more general viewpoint, stipulations generally are not true or false. I mean, this is something that we learn from philosophy of language, but useful or useless. So, I mean, if I'm right that at least some of the philosophically interesting symmetries that we consider in philosophy of physics, but also in philosophy of science, are stipulations. And I'm mainly referring to space-time symmetries and also time reversal invariance in particular. So I don't see how you can be realist about these symmetries, how you can say that they are playing a role in describing the ontology. So again, this is not a knockdown argument, but at some point I think that it makes the symmetry realism attitude a little bit less appealing than before. So now let me very quick go for the alternative proposal, that is symmetry deflationism. That is an alternative that I'm trying to think about to construe the role of, to construe a way to say symmetry that make justice to the idea that symmetries are fundamental. So I want to retain the fundamentality of symmetries, but to resist the realist attitude. And let me go very quickly through this. So what I would say is that, okay, fundamentality could be said in two different ways. We can think of symmetries as fundamental because they are fundamental in ontology, but also we can think that they are fundamental in the representation of ontology, like playing an epistemic role. And we want to be fundamental about this because it's the way in which, for example, or it's an ineliminable feature of modern physical theories that we want our physical theories to have, but we don't need to say that they are also fundamental in ontology. They are playing a different role. We can think that physics needs symmetries as a way to formulate good physical theories, but there's no need to say that this fundamentality is justified because it's capturing some fundamental feature of the world. So we can construe symmetry deflationism through this idea of epistemic fundamentality. This implies that metaphysically, I mean, this implies something like metaphysical democracy in the sense that, okay, symmetries come in many flavors, but from the metaphysical point of view, all of them are equal. Differences among symmetries are representational differences, but not ontological ones, because they are not part of the ontology. They are part of our models, of our equations, playing a probably super useful epistemic role, but they are not really representing something in the ontology. And again, if they are not playing a representational role, probably we shouldn't ask, what does asymmetry represent? We should rather ask in this Sidney plan style, what facts about theory construction and experimental practice may require the postulation of symmetries and how they play such role? And I think that this is the right question that we should make to the symmetries, right? Not the idea that, okay, whether they represent or not, but what facts about theory construction and experimental practice they make possible. And about the heuristic role, I already said a lot of things about this, but the idea is that, okay, they probably play a very useful role in simplifying dynamical problems or in giving us better physical theories, but this shouldn't be confused with ontological problems or with ontological claims. Okay, and again, this is something that I already said, but probably there is a way to make sense of symmetries in the sense of meta laws, but now in this more epistemic way, in which they are just constrained the way in which can formulate the laws. They are not just meta principles in ontology that are giving us a logic of nature, that something that sometimes is said, but they are just guiding us in a way to formulate the dynamics in a more effective, more informative, or simpler way. In this sense, I think that they could very well play the role of meta laws, as in Dürr and Teufel's quote. But this is what is important, and I'm just almost done. That now, if we take symmetry deflationism seriously, it seems that now the symmetry-to-reality inference we start with in this presentation is no longer so appealing, because now any statement about symmetries is a statement about how to represent physical theories. It's not a statement about the ontology that the theory is trying to represent. It's about our epistemic resources to build better physical theories, but it's not about how we can capture the ontology in a better way. So now, I mean, if we look at the symmetry, I mean, if we accept something like symmetry deflationism, I don't quite see how we can now make this connection between symmetries on the one side and an ontological problem on the other side, because the inference at some point requires at least a minimal realist reading of symmetries. But I already mentioned some problems I saw. But if we adopt symmetry deflationism, well, I don't see how to make how we can put this inference to work. So, final remarks and the general view. We start with this problem, the philosophical problem of the time direction and the formulation in terms of symmetries, time reversal symmetries. I argue that, okay, how we can implement time reversal symmetry, in particular time reversal, depends on a concept of what's meant by reversing time. And I say that the concept depends on a philosophical framework. So if we want to make sense of the idea of this inference we start with, we need to give all this background. But now when I see that the problem from outside, I see that if we are really symmetry deflationist and we don't think that symmetries are playing a role in the ontology, but they are playing a more heuristic epistemic role, even though it's quite fundamental, then I'm not quite sure how to make this first connection. So probably many of the discussion about time, about space, well, depends on a particular view about symmetries in general, as physical resources to think about the metaphysics, but also to think about the ontology. So now I am trying to work on this and trying to develop these arguments further. So thank you very much for hearing.
Thank you so much, Cristian. That was